Okay, so I have the pleasure to introduce Anitha Andiappan. Anitha studied chemical engineering at the National University of Singapore and ETH Zurich. During her studies, she worked as a research assistant on heterogeneous catalysis of methane at ETH. In 2010, Anitha started working with Worley Parsons as a process engineer in the hydrocarbons team, tackling various downstream and upstream projects. She then completed her master's in petroleum engineering, specialized in reservoir engineering at the Montaigne University of Leoben in Austria. Anitha joined ROG Austria AG in 2014 as a reservoir engineer in the subsurface team. Her work includes the management of gas reservoirs in Upper Austria, as well as developing and managing underground gas storages. Furthermore, she engages in renewable energy projects with her subsurface expertise, such as hydrogen storage in natural gas reservoirs. In addition, she is a visiting lecturer at the Montaigne University of Leoben in Austria. Anitha, we are very much looking forward to seeing this magical slide that is not
That
transparent.
didn't work. Thanks for your patience. Thanks for the introduction, Hadi. Today I'll be talking about the underground hydrogen storage in porous rock. And this is the Rubensdorf field that some of y'all from the audience were present at the inauguration ceremony in April this year. So why hydrogen storage? That was already today in the morning session I saw, so I won't waste a lot of time here. But just a quick, to show you the supply-demand, how it looks, the forecast scenario in Austria, which shows daily time in y-axis and also the months. What you see here, these red parts are the surplus in energy amounting to about 12,000 megawatts that comes in the summer, autumn, and spring months. And then you have an energy deficit in the winter months amounting to about minus 8,000 megawatts. And this calls for the need of a seasonal storage. As of now, we have seasonal storage in the form of natural gas. However, for a sustainable energy future, this energy should be coming from renewable energy sources. And one solution would be to have energy in the form of hydrogen. And how can I store? What are the storage options I have for underground for hydrogen? And I could either have it in salt caverns, as we heard before, that makes up about 20% when I compare to existing UGS in EU, and the rest, 80% roughly, from porous rock, either aquifer or hydrocarbon reservoirs. Of course, the question then comes, is it safe, feasible? What about my leakage? What happens to my hydrogen in the reservoir? And this is what we, RAG, went on investigating in hydrocarbon reservoirs, especially particularly depleted gas reservoirs. So we, RAG, have the facility or underground gas storage operator. And in 2015, we started with mixtures of hydrogen and methane gas storage. That's the Leyen field. And many of you all maybe know underground sun conversion. And there we stored hydrogen produced from a 0.5 megawatt electrolysis unit. And this is what I'm presenting mainly from then on till now, the results that we have obtained or findings, know-how from 2015 onwards in terms of ranging from material behavior, geochemistry, flow and porous media, what does H2S look like? And then the 100% hydrogen storage, which is the Rubensdorf field. So important, is the material that I'm using in my facility resistant to hydrogen? And what do we know till now? Or initially when we started, we said we did laboratory experiments with various type of steels. I'm not going into the detail and tested up to 100 bars and 80 degrees Celsius in wet and dry conditions. And then it came out that L80 was the most suitable, and that's what we are using now. And we also tested the elastomers that we use at 100 bars and 80 degrees Celsius. And with this, then we went to the field and in the previous project, and we have a test section. I don't know how clear is it, so you have 3 parts, and this is connected to the gas string going into the well and also coming out of the well, and 3 sections so that in one I can have my steel. This is an example of the pre-stretched steel, and on the second one then a cement sample, and also in the third one elastomers, and these are the elastomers, 15 types of elastomers that we usually use. And what were the so we then left it in the project and compared how it looked before and after exposure, after the gas came out from the well. And the changes monitored in the laboratory here were similar or comparable to the ones that we obtained from the field. With this said, the materials that we have picked indeed is adequate for H2 hydrogen operation. Then I come to the geochemistry part. How does the chemical integrity look like in the reservoir? It also came out in Silka's as the top thing, caprock integrity, that also is covered here. So I'll touch first about the reservoir rock integrity. In the project, we have a representative reservoir rock from the Molassa Basin, that's where we operate, and we tested in the laboratory with up to 75% of wet hydrogen. And on the left, there are thin sections before exposure to hydrogen and after 12 months of exposure to wet hydrogen. And there were no reaction seams, so the corners were still very edgy. That then suggested there were no hydrogen-induced changes. And in the field, we conducted with up to 20% of hydrogen mixtures, admixtures, and this also, we have the results showing that the behavior is similar as expected in standard natural gas storage operations. How do we know? Because we compare the permeability through pressure transient analysis from time to time. And then caprock integrity. We've done laboratory tests with dry hydrogen and methane in a representative caprock, again in the Molassa Basin, where we operate very close to the fields that we have now chosen, Lehen and Rubensdorf. And the permeabilities of methane and hydrogen on the right, as you can see, they are in the same order of magnitude, suggesting that a caprock that is able, in our case, that is able to store methane or natural gas is also able to store hydrogen. However, there are some small aspects that we feel would close, or there are still some open questions, I would say. How would caprock and reservoir rock behave when exposed to 100% of wet hydrogen? And this is what that we are looking now in the current project in Rubensdorf with our partners. Then I come to the topic of flow and porous media. So how does hydrogen move and mix in the reservoir? In the first project here in sun storage, you see in the y-axis the amount of hydrogen volume inject, and in the x-axis the number. The x-axis the number of days. So we injected a total of roughly slightly below 120,000 cubic meters of hydrogen, and we retrieved slightly above, so about 80% of the hydrogen injected. So then, of course, the question came: what happened to the remaining 20%? And what are the physical processes that could be here? I'm not talking about the biochemical, because then I need another 20 minutes time. But so talking about physical processes, dissolution, diffusion, and these are the things that we started off 10 years ago. And so we first looked at dissolution, and we had the solubility of methane and hydrogen modeled in FRIXI, the freeware, based on data from literature, which were calibrated based on literature data. And what we noticed was the solubility of the hydrogen is way less than that of methane, and additionally with increasing salinity that the solubility of hydrogen decreases. So then if this is not the major thing, then we asked ourselves, what else could it be? Then we went on to diffusion. I specifically wrote here diffusion gas to gas, because when you have gas to water phase, then you have the dissolution effects overwhelming. So then for this, we had laboratory experiments in the Montagne University of Leoben. So this is basically a sketch of very simple 2 sand packed columns, homogeneous sand, one filled with hydrogen, one filled with methane, and it was then we looked at when the first molecules of hydrogen reached on the other sandbag column, and it took about 4 days for the first molecules to reach, and this experiment is conducted at 4 bars. And for a complete mixing of hydrogen with methane, only with diffusion was calculated to take about 1 year. And this is at 4 bars and a homogeneous sand. And most reservoirs are heterogeneous and operate at way much higher pressures. With this, it was then for us quite clear that these contribute also minimal effects to the flow in porous media. However, in the field test, when we drilled the other well in Leyen, we noticed that there was a fast breakthrough of hydrogen on the other well. So then the question came, what could it be? And this is something that we are looking at. We think it could be dispersion because of the finger flow that you could have in a reservoir, and dispersion coefficients are generally much higher than that of diffusion coefficients. So yeah, with that I come to the potential of H2S generation. That's the other topic. We all know H2S is a hazardous gas, and that's why it is also labeled by the EU regulation, and there are emission standards for these. And the question is, could hydrogen react with the dissolved sulfur or sulfur-bearing minerals? And if it does, then how does my H2S emission look like? What do we know till now is we had in the underground sun conversion in Leyen field H2S concentration monitoring, and during the injection and withdrawal, and this had up to 20% of hydrogen admixtures. And what you see here is basically the value that we got from the gas chromatograph at the outlet of the well, and what is going at the inlet. So you have hydrogen share in milligrams per norm cubic meter, and on the x-axis you see the turnover volume. So this is an injection, and then you have the withdrawal. So this is of one injection withdrawal cycle. These red arrows are anomalies. These spikes are due to calibration of the GC, the gas chromatograph, as well as a sudden start and shutdown of the facility, and then you have the restart. But generally what you see here is that during injection we have about 0.25 milligrams per norm cubic meter of H2S in the gas, because the natural gas is coming from our facility, which has this small amount. And then during withdrawal, it increases. Yes, it does increase. And we are below 2.5 milligrams per norm cubic meter, which is way below the EN European norm of 5 milligrams per norm cubic meter. However, we would like to know how does the H2S development look like when I store 100% of hydrogen in the reservoir. And this is a metagenome that we have of the microorganisms in the field, the Rubenstorff field. And this small pie here, this part, this Lieni, seems to be, or from literature suggests that it could act as a proxy for a possible H2S generation through biological pathways. And for this, we have lab experiments with our partner Boku, Ifatul, mimicking the in situ conditions and also monitoring how the microbial consortium changes. So we have taken water sample at the beginning of and we'd like to take one after one cycle and at the end of the project, and to compare them as well. Correct. And then I come to storing 100% of hydrogen. And this is now the Rubenstorff field here. And this would be storing hydrogen coming from a 2 megawatt electrolysis unit. Just quick facts and figure. This is a depleted gas reservoir using 2 megawatts of electrolysis unit. The working gas volume that we are planning to have here is about 1.2 millions of norm cubic meter, and in the rate of 400 to 600 norm cubic meters per hour. The operating reservoir pressure during the working gas volume would be about 56 to 76 bars. And we have also started the building of 8 kilometers of hydrogen pipeline that connects this field to our facility, where we would be using to combine heat to electrify the facility. And then I would like to show a small video if that works. Yeah, no sound? You have to escape probably, yeah?
Yeah, now it's okay.
It worked just now. Oh, yeah.
We don't have sound.
Here maybe. Okay. Yeah, I just wanted to show the Rubenstorff field, but it's okay. Then I come to my final slide. With that, I've saved time. So what do we know till now? Our findings suggest that the materials used are adequate for hydrogen operation. There are no negative effects on the reservoir integrity. The cap rock remained intact with dry hydrogen. And the experiments show that dissolution and diffusion are minor contributors to flow effects. And there are minimal amounts of H2S production thus far. However, we have some open questions that we'd like to answer, such as how does the cap rock as well as the reservoir rock behavior when exposed to 100% of wet hydrogen, and what are then the major contributors for the flow effects, as well as how would the H2S production look like with 100% of hydrogen storage. With that, I end my talk. Thank you.
Was it the same video as Stefan showed last year, or is it updated? Do you know?
No, this is from the new one, from the field.
So we will send it to you. We will send the link to you later on. So Catherine, and then I go. Okay.
Oh.
Thank you. Thank you for a very comprehensive talk with a lot of things that you looked at. I'm interested in the reactions with the cap rock or the reservoir rock materials. You showed thin sections. Did you do any mineralogical characterization? Like what were your expectations about what minerals there would have reacted? Yeah, that's in the experiments where you were measuring permeability to look at if there was permeability change.
Correct. This is, so, I mean, when I do permeability through pressure transient analysis, I can't look at a micro level. But I roughly see before injecting with hydrogen how my permeability of my rock was, and after that, and I expect no changes. And they should stay roughly about the same. And it did over the years in the other reservoir. And with cap rock, we did this, we put them in autoclaves, bare, and then 3 months, 6 months, and also in dry condition and also in wet, so with brine and with our brine recipe. And we have XRDs in the current thing. We have XRDs of the previous one, and we'll also do of plugs with after as well to see, but they are very correct to see how the percentage changes with XRD.
Thank you, Anita, for your presentation. I'm Ahmad from Heriot University. I have a question. Have you observed any methanogenesis in this project, and what is the type of mineralogy in this test? Thank you.
So, I did not specifically go into methanogenesis because that would come under physical reactions, and yeah, there are geochemical reactions. And we did notice methanogenesis, and we see that CO2, in our case, seems to be the limiting factor. So once your CO2 that you have in your natural gas, in our case actually, that once it is converted, it could be acetogenesis as well, or methanogenesis, then the process stops. That is correct. And the mineralogy, it's basically mainly quartz sand, yeah.
That was David.
Hi there, I'm David from Naples. Couple of questions. What was the temperature at the reservoir when you injected your experiment? Was it the deposit a pure sedimentological with no fracturation inside?
The first question, I didn't quite get your second question. I'll just finish the first one. The temperature that we have is about 34 degrees. Yeah.
Okay.
Very low.
The second one, have you had any previous microfracturation within the reservoir when you are
No.
you selected? Okay.
Because we don't go above initial pressure.
All right. And after the experiment?
Also not, because we are operating below the initial pressure
All
of
the
the
time.
reservoir at all.
Thank you very much.
Okay, let's thank Anitha one more time.